Welcome to Thermodynamics lecture series. In the present lecture, we will discuss the energy interactions. In thermodynamics, energy interactions refers to how energy is transferred between a system and its surroundings. And energy is transferred between the system and surroundings by in the two modes. One is the heat energy transfer, another one is the work energy transfer. Let's see the heat energy transfer. Heat is in the form of energy that is transferred between a system and its surroundings due to a temperature difference. So heat energy will be transferred between the system and surroundings due to a temperature difference. Next we have to see the work energy transfer. Work is the energy transfer that occurs when a force is applied over a distance, or more broadly any energy transfer not caused by a temperature difference is called as the work energy transfer. So in the work energy transfer, so the energy will be transferred due to the when you have to apply the force over a certain distance, or maybe any energy is transferred not caused by a temperature difference. If the energy is transferred due to the temperature difference, we are calling as the heat energy transfer. Similarly, energy is transferred not caused by a temperature difference, we are calling as the work energy transfer. A closed system can interact with its surroundings in two primary ways. One is the through work transfer, or maybe the through heat transfer. This form of energy exchange are known as energy interactions. So energy interactions mean, so energy will be exchanged between the system and surroundings in the two modes. One is through the work energy transfer, or maybe through the heat energy transfer, and they lead to changes in the properties of the system. In thermodynamics, focus on studying these energy interactions and the resulting in changes of the system's state. Let's see the work energy transfer. Work is the one of fundamental modes of energy transfer. In mechanics, work is defined as the action of force applied to a moving body. A force serves as a means of transmitting an effect from one body to another. An effect such as lifting a weight through a certain height can be achieved either by applying a small force over a large distance, or a large force over a small distance. So we know that work is the product of force into the distance. Let's consider when we are lifting the weight here, this can be achieved by small force into the large distance, or maybe large force through a small distance. In both cases, the product of force and distance remains the same to accomplish the same outcome. So in mechanics, work is defined as the work is done by a force as it acts upon a body moving in the direction of the force. So the product of the force and distance moved parallel to the force is the magnitude of the mechanical work. So now see the work transfer in thermodynamics point of view. In thermodynamics, work transfer is viewed as an interaction between the system and its surroundings. So in the mechanics point of view, work is defined as the force over a certain distance. In thermodynamics point of view, work transfer is viewed as an interaction between the system and its surroundings. So work is said to be done by a system when its only effect on the surroundings is equivalent to raising a weight. These weights may not be actually raised, but the effect can be equated to raising of the weights. So let's see the one small example to elaborate this definition. So let's consider the battery and motor as shown in the figure. So in the figure we have to observe that one the motor is driving a fan. So here system is doing the work upon the surroundings. So here system we are considering the battery and the motor, and this system is doing the work upon the surroundings. Here surrounding is the fan. Similarly we have to refer the figure 2. So when the fan is replaced with a pulley driven by a motor, so the sole effect on the things external to the system is then the raising of a weight. So let's compare with the figure 1 and figure 2. We are replace the pulley and weight with the fan. So in the first one, in the figure 1, system is doing work upon the surroundings, which means the motor is driving a fan. But in this example, in the figure 2, we have replaced the fan with the pulley. Here, so sole effect of this system is rising of the weight. So next to see the conversions of work transfer. When the work is done by a system is taken to be a positive, and when work is done on a system it is taken to be a negative. So in the figure A it is representing the work is done by a system on the surroundings. So work done by the system on its surroundings. So work is positive. Similarly, we have to observe the figure B. Here work is negative because work is doing from the surroundings on the system. So work is we are taken as the negative. And the unit of the work is Newton meter or the joule. Next we will discuss the generalized situation for non-flow work or closed system work. So have to consider one closed system. So here in this example we are considering the closed system is the piston and cylinder, and gas is enclosed in the cylinder. So let the gas is enclosed in the cylinder be the system. So which is representing in the figure. Initially at pressure P1 and the volume V1. So initially we are considering the pressure of the gas is P1 and volume of the gas is the V1. The system is in a state of thermodynamic equilibrium, which is fully defined by the coordinates of P1 and V1. So this is the condition. So initial condition and considering the state 1, and in this condition so system is in thermodynamic equilibrium, and we are defining by the two coordinates, that is the P1 and V1. The piston serves as the only movable boundary responding to the pressure exerted by the gas. So when the pressure exerted by the gas, obviously piston it will be moved to the another state. Suppose the piston moves outward to a new final position labeled to state 2, which is also a state of thermodynamic equilibrium characterized by a pressure P2 and V2. Now system is moving to the another state. So in this condition, in the equilibrium condition, so pressure and volume of the gas is P2 and V2. At any intermediate piston during the piston's motions, let's consider the pressure is the P and volume is the capital V. When the piston moves an extremely small distance, let's consider dl, and small a is the area of the piston, then force capital F acting on the piston equal to the P into A. Here P is the pressure of the gas and A is the area of the piston. And the extremely small amount of work done by the gas on the piston, so which is equal to the, so let's consider the small amount of the work, then dW equal to the force into distance F into dl. We know F equal to the PA, then dW will become the PA dl. We know that one, the A into dl is the volume of the piston, then dW equal to the, so P dV. So where the dV equal to the A into dl, which is the extremely small displacement of the volume. When the piston moves out from the position 1 to 2, with the volume is changing from V1 to V2, then amount of the work capital W done by the system will be equal to the, so work done from the position 1 to position 2. So work done W, so 1 to 2 equal to the integration of PdV, so with the limits of V1 to V2. This magnitude of work done is represented on the curve as shown in the figure. So in the figure it is observed that volume is represented on the horizontal axis and pressure is represented on the vertical axis, and piston is moves from the state 1 to the state 2. In this regard, pressure is changes from the P1 to P2, which is decreasing. Similarly, volume V1 is changes from V1 to V2, which is the increasing, and the amount of the work done is representing the area of the under this PV curve. So let's consider the, since pressure small p remains a thermodynamic coordinate throughout the system and it must be pass only through the equilibrium states as the volume changes from V1 to V2. So this is required a path 1 to 2 to be a quasi-static. So the piston moves infinitely slowly to ensure that each intermediate state is in the equilibrium. So while the piston is moving from the 1 to 2, then in the all the intermediate states are the equilibrium states and the path 1 to 2 is the quasi-static. And the integration of PdV can be performed only on a quasi-static path. So we know that one, the, so work is the integration of PdV for the non-flow work or maybe closed system work, and this work done is the area under the curve of the PdV. So amount of the work we can be say that one, the product of the PdV and area equal to the work done. And condition for applying the equation, so W equal to integration of PdV, there is the three conditions are there. First one is the system must be a closed system, work should cross the boundary, and the process must be a reversible process. So it is the quasi-static process. Next we will discuss the path function and point functions. First we have to see the point function. A point function is a thermodynamic property whose value depends only on the state of the system, not on the path taken to reach that state. So in the point function, values are depends only on the state, not on the path. So it is defined at a particular point in the process. For examples, pressure, volume, temperature and internal energy, enthalpy and entropy. So these are the examples for the point functions. So remember all these properties. So these are the very important for the objective point of view. Change in a point function depends only on the initial and final state, and these point functions are the exact differentials, which mean so V2 minus V1. So the difference between the final and the initial, we have to say that one the V2 minus V1, or maybe the T2 minus T1, or maybe P2 minus P1, U2 minus U1. So the differences, so final state and the initial state, we have to say that one these are the exact differentials. These differentials of point functions are exact or perfect differentials, and the integration is very simple. Next we will discuss the path function. A path function depends on the specific path followed during a process between the two states. It is defined only during a process, not at a state. Examples of the path function are heat and work. Path functions are not exact differentials and are usually written with delta, not with the d. Examples, delta q or the delta w. Their values depend on how the system moves from the one state to another, not just on the end points. For example, let's consider the work done during the change of the state 1 to 2. So work done from the 1 to 2 is not a W2 minus W1, and it is the delta W, not the dW. But in the case of the volume, we can be written as V2 minus V1, and it is equal to the dV. So the differences between the point function and path functions are the, in the point function, so depends only on the initial and final states, and in the path function depends on the how the path is taken. Example of the point function is internal energy, and path function examples are the work and heat. And point functions are the exact differentials, but path functions are the inexact differentials. Next we will discuss the why we work as a path function. In thermodynamics, work is considered a path function, not a state function. This means that the amount of work done by or on a system depends on the specific path taken during a process, not just the initial and final states. With reference to the figure, it is possible to take a system from state 1 to state 2 along the many quasi-static paths such as A, B or the C. Let observe the figure here represents the state change from the 1 to 2 by different paths such as A, B and the C. Since the area under the each curve represents the work for the each process, the amount of work involved in each case not a function of the end states of the process, and it depends on the path of the system follows in going from state 1 to state 2. We know that work done is equal to the area under the PV curve. So area of the PV curve with path A is different and area under the PV curve with the path B is the different, and similarly area of the PV curve with the path C also different. So work done also varies with its varying of the path. So work done is not depends on the end states of the system. For this reason, work is called as a path function, and dW is an inexact or imperfect differentials, which means integration of 1 to 2 dW is not equal to the W2 minus W1, and integration of dW 1 to 2 equal to the W1 to 2. Next we will discuss the closed system work for the various processes. First one is the constant pressure process. So this is the PV diagram for the constant pressure process. Here is system is changing from the one state to another state, that is the state 1 to state 2. So in the state 1, so pressure is the, let's consider the P, and volume is the V1. In the state 2, volume is the V2 but pressure is the same value P, because process is the constant pressure process, and we know that one the area under the PV curve is the work done. So next we have to see the amount of the work done in the constant pressure process, and we know that one the work done, so from the state 1 to 2 is the W1 to 2 equal to the integration of PdV V1 to V2. So here P is the constant, then this is taken out from the integration, then W1 to 2 equal to the P integration of V1 to V2 dV. So this can be written as, so W1 to 2 equal to the P into V2 minus V1. So this is the amount of the work in the constant pressure process, so which is equal to the area under the curve. So next we have to see the another process, constant volume process. So here observe the PV diagram. So now the system is changes from the state 1 to state 2. So let's consider pressure at the state 1 is the P1 and V volume is the V, and similarly pressure at the state 2 is the P2 and volume is same amount, that is the V. So volume is the constant, so volume is not changing, so volume equal to the constant, and it's a differentiate V2 minus V1. So here V1 value as well as V2 value same as the V, so it is equal to the 0, and we know that one the work done, so state 1 to state 2 W of 1 to 2 equal to integration of P dV, here dV value is the 0, then work done in the constant volume process is the 0. Next we will discuss the constant temperature process. In this process temperature is the constant, and we know the ideal gas relation, that is the PV equal to mRT. Here M, R and T are the constant, then PV equal to the constant, that is PV equal to C. From this relation we can be say that one the P equal to C by V, and observe the figure. So this figure represents the process in which PV equal to the constant. Here system changes from state 1 to state 2, and let's consider P1 is the pressure at the state 1 and V1 is the volume at the state 1. Similarly P2 is the pressure at state 2 and V2 is the volume at the state 2. and this PV curve is the PV equal to constant curve, and this is changes with the rectangular hyperbola. Next we have to see the work done in this process, that is the W122 equal to integration of PdV with V1 to V2. So here, so P can be written as C by V, then W122 equal to the integration of C by V dV with V1 to V2, and C is the constant, and bring outside from the integration, then W122 equal to the C into integration of 1 by V dV V1 to V2. This can be written as W122 equal to the C into ln V2 minus ln V1, and this equation we can be written as W122 equal to C into ln V2 by V1, and we know that PV equal to the constant, then P1 V1 equal to the P2 V2 equal to the constant. Then this C value we can be written as P1 V1, then substitute in this equation, then W122 equal to the P1 V1 ln V2 by V1, and this can be written as W122 P1 V1 ln P1 by P2, and also written as, so W122 equal to P1 V1 equal to the MRT, so W122 equal to MRT ln P1 by P2. Next we will look for the adiabatic process. A process is said to be adiabatic process in which there is no heat transfer from the system or to the system. So in isothermal process, temperature remains the constant, delta T equal to the 0. In the adiabatic process, heat transfer is the 0, which means no heat exchange with the surroundings, Q equal to the 0. So in the diagram is represents the adiabatic process. So in general we are calling as the adiabatic process mean which the relation is PV power N equal to the constant. So this is the diagram for the adiabatic process. So here when N equal to the 0, then from this equation it will become P equal to the constant. So same thing here, from state 1 to state 2 pressure is the constant. And similarly N become the infinity, then it is the volume which is the constant volume process. And PV power N equal to the constant mean it is the adiabatic process. So here N is the adiabatic index and it is greater than the 1. And from this relation we can be state that one PV power N equal to P1 V1 power N equal to the P2 V2 power N, and P is the P1 V1 power N divided by V power N. So next we determine the work done during the adiabatic process, that is the W122 equal to the integration of V1 to V2 PdV. Here P is the P equal to the C divided by V power N. Then work done W122 equal to the integration of V1 to V2 of C by V power N dV. So here C is the constant, bring outside from the integration, then W122 will become the C integration of V1 to V2 1 divided by V power N dV, and this will become the W122 equal to the C into V power minus N plus 1 divided by minus N plus 1 V1 to V2. This will become the W122 equal to C divided by minus N plus 1 into V2 power minus N plus 1 minus V1 power minus N plus 1, and this can be written as W122 equal to the, so 1 divided by minus N plus 1 C V2 power minus N into V2 minus C V1 power minus N into the V1. So from this one C V2 minus N will become the P2, and similarly C V1 power minus n will become the P1. So then equation can be written as W122 equal to 1 divided by minus n plus 1 into P2 V2 minus P1 V1. So this can be written as W122 equal to, so take the minus, then it will become the minus of P1 V1 minus P2 V2 divided by minus of n minus 1. So here minus will get cancelled. Then W122 equal to the P1 V1 minus P2 V2 divided by n minus 1. So this is the work done for the adiabatic process. So next I have to look for the polytropic process. A process is said to be polytropic process in which pressure and volume follows the relation of the PV power gamma equal to the constant, where gamma is the polytropic index and this gamma equal to the Q0 divided by Cv. Generally, gamma value is varies from the gamma is greater than the 1 and the gamma is less than the L. And this is the relation between the gamma value with the type of the process. If the gamma value is the 0, the process we are calling as the isobaric, which means constant pressure process. Similarly, if the gamma value is equal to the 1, the process is the isothermal process, where the constant temperature. If the gamma value equal to the n, the process we are calling as the adiabatic process, which means there is the no heat transfer. And similarly, when gamma equal to the infinity, the process we are calling as the isochoric process, which means constant volume process. And work done in the polytropic process is the, so W122 equal to the P1 V1 minus P2 V2 divided by gamma minus 1. So this is the work and energy transfer and work done for the various processes. And thank you.